Что-то я прямо уже в интернет?
Сейчас посмотрим.
Просто нулевые криминологии пространства.
Так, у нас...
Я думаю, под этой фразой все-таки есть физическое
там,
можно сказать, там, течение восстановления, там, еще что-то. Там калибровочные какие-то связанности и связанности.
Да что видно? Можно миллиметр сдвинуть камеру направо, да?
Вы видели эту камеру вообще?
Нет, это вроде идеально.
Я думаю, что лучше ее не трогать. Так, единственное, что я сейчас выйду, вас послушаю, потому что звук не слышно. Если я не вернусь, значит у вас все
Хорошо, спасибо.
В конце нужно остановить трансляцию.
А в конце как что сделать? В самом конце? Что
Остановить трансляцию. Остановить трансляцию. Нулевые криминологии.
Остановить трансляцию, закрыть это, закрыть ключи.
Нет, это мы сложно, естественно. А с компьютером закрыть ключи.
Вы закрываете все, потому что вы так оставляют непонятно, как все сбивается.
Если остановить трансляцию, то она на YouTube останавливается.
Да, на YouTube не надо ничего делать.
А если опять включить, то это уже будет новая трансляция на YouTube.
Не будет трансляции, потому что если вы хотите сделать перерыв, лучше ничего не делаете. Там где-то можно нажать паузу, но я не помню, что где лучше ничего не делать.
Понятно, спасибо.
Можете чуть-чуть окно прикрыть, пожалуйста? Или дверь закрыть?
Дверь закроем,
Говорю.
Меня не слышно? Звуки работают. Говорю что-нибудь. Ничего не слышно? Нет? Слышно? О, отлично, спасибо. Okay, so let's start our offline class. And we'll have some examples of schemes. The very first example, say, the project, or maybe even the affine line over real numbers. So let's discuss what are the points. And what's your name?
My name
Yes?
is Iju.
Ah, nice to meet you. Just describe all the points. First of all, there is the generic point. Sorry, eta, right? And this is the spectrum of the field R of T, right?
What is R?
R is the real numbers. Okay, so this is the most thick point, and everything else lies in its closure. But what is everything else? Any examples of other points? Vanya? Just one point, huh? Right, absolutely. Real points. So A. So there is just the real line. But that's not all. There is something else. So Leonid, what are other points? I mean, the points are just prime ideals in the ring like this, right? So what are the prime ideals? Vanya says that there are ideals like T minus A. Very good. They are. Huh?
Irreducible polynomials.
Right. So there are complex points. Namely T minus, say, Z times T minus Z bar. Yes, where Z lies in complex numbers, but not real. Okay?
About the generic point, is this,
Yes.
it corresponds to the zero ideal?
Right, absolutely. Absolutely, right.
Why do you note it as spectrum of R of T? What is R of T? Is it
It's the field of rational functions of one variable with real coefficients. Right?
P is ideal in what?
Well, but by definition, when we can this thing is the spectrum of the ring of polynomials in one variable. But the ground field is now real numbers. We used to have algebraically closed field K before, but now it's not necessarily algebraically closed. Well, there are many types of schemes, but the simplest one we didn't consider yet is almost the same as before, only the ground field is not algebraically closed.
Once again, why do you identify the generic point as the spectrum of the field?
Because it is ringed, right? The whole thing, the whole spectrum is ringed, and in particular, each point is ringed. So, what is the ring corresponding to this point? It is just the ring of rational functions.
So there's a localization by the
Right, absolutely. You just take R of T, then you localize it at this ideal. Oh, sorry, polynomials. Then you localize it at this ideal, right? And then, if you want to know the residue field, you take this is a local ring, and you take this local ring modulo its maximal ideal. But in this particular case, this localization is just the field already. There is nothing to be done.
Once again, why to take the residue field?
So each point like P in the spectrum of whatever field R gives rise to the local ring. R localized at the ideal P. This is the stock of the structure sheaf at this point P. Okay, and the residue field Kp by definition is this local ring modulo its maximal ideal. By definition, this is just terminology, notation.
This is a fiber of this structure.
Yeah, this is not the stock but the fiber. such a sheaf at P. Okay, so this is some general terminology, but in this particular example, we have like three types of points. Yeah, there is the. We're classifying all the prime ideals. There is a prime ideal like this. The prime ideals in the polynomial ring are the same as irreducible monic polynomials. And they are either linear or quadratic if your field is real numbers. This is the complete classification. So these are complex points where the residue field is C, and these are real points where the residue field is R. And there is a generic point where the residue field is rational functions over R. Okay? Well, say uniform description. So we start with this ring R, but then we can go to the complex version, just we complexify. Oh, sorry. Okay, the complexification. And then the spectrum of this complexified ring is something well known. So it's the thick point, the generic point like this, and also the complex numbers. All the prime ideals are linear
What is R
polynomials.
once again?
R is our ring. Oh, sorry, Blin. Where are we? Yeah, this is R. Yeah, sorry. Okay.
R is a ring over real number.
Right.
Real number.
And then we complexify it. So we go to the algebraically closed field. Then we already are very well used to this situation. We know all the points of the, for example, of the affine line over algebraically closed field. Yeah. Now for schemes we just add one more generic point and that's it. But now on this thing there is an action of the complex conjugation.
So this works only for one ring?
Yeah, only for one ring. But it works the same way for all the other rings. Okay, so there's an action of complex conjugation of Galois group of complexes over reals. And the spectrum of R is the spectrum of its complexification modulo complex conjugation. So the spectrum of R is the set of sigma orbits in the spectrum of its complexification. Okay, some orbits consist of 2 points, some orbits consist of 1 point, like this. And the generic one also consists of 1 point. And this is absolutely general, so for any real ring, well, for any, say, R algebra R. Hello, are you Wei Chen? Nice to meet you. For any algebra R, the spectrum of R is the spectrum of its complexification modulo the complex conjugation. The orbits of complex conjugation on its complexification spectrum. Okay, and in fact, for any scheme at all, say S over R, and what does it mean? it means that we have a morphism from S to spectrum of R. Morphism of schemes. There is a notion of complexification. SC is just the Cartesian product S over spectrum of R times the spectrum of C. Yeah, there's this Cartesian product. We had it, well, maybe in the absolute situation, but it works the same way in the relative situation. And then the points of our initial scheme are just the conjugation orbits, sigma orbits, in the set of points of the complexification. And the sigma acts just on the second factor. So there is yeah, this is the only automorphism of the spectrum of C over the spectrum of R. So it's just one point, but this point is ringed by complex numbers. And so there is this automorphism. Okay. So that's how it works for real numbers, and very similarly it works for finite fields. Now we replace real numbers by some finite field Fq, and we replace C by the algebraic closure of Fq. Yes.
Sigma is morphism of scheme.
Automorphism of the scheme, yes.
Automorphism of the scheme,
Mhm.
not an automorphism as a C-ring space.
Well, the scheme spectrum of C is just one point, but it is ringed with the field of complex numbers. And as such, it has an automorphism. It acts trivially on this point, but it acts non-trivially on the ring.
This is a scheme over C also.
Absolutely.
This morphism is not.
No, it is not. No,
But it's compatible with this.
but it is a morphism over R. Mhm. No. Okay, and the complex conjugation corresponds to what? Daniil? So it is generated by what? Yes, by Frobenius. This Frobenius takes z to the power q. Q is the cardinality of this field. Okay. And so the same holds true. If you have any scheme X over Fq, then it gives rise to X bar over Fq bar. And now here we have the action of Frobenius. And there's a standard notation X is the set of closed points of X. Okay, so X is the set of closed points of X bar modulo Frobenius. So the set of Frobenius orbits in the set of closed points of this extended scheme. But extended scheme is just the usual algebraic variety in our usual understanding because of our algebraically closed field. So then probably you have some intuition how to think about it. And the intuition for schemes over finite fields are just Frobenius orbits in the algebraic varieties over its algebraic closure.
This is the definition.
Definition of what? No. How do you mean? We have this abstract notion of schemes. So it is glued out of affine pieces and so on and so on.
The closed points correspond to the maximal ideas.
Yes, absolutely. Yes.
So or topologically, they would be just points that are closed.
Yes. Everything is true. Yes. If it's spectrum of a ring, then the closed points correspond to maximal ideals. Yes. It's not necessarily spectrum of a ring. It could be projective variety or whatever.
Generic point is not a closed point.
No. It contains everything else in its closure. Okay. Okay. So now, yes.
Have the same operation like complexification over.
I can't hear you. Sorry.
Is R by FQ, C by FQ bar.
Yes.
So when we consider the case in R, we have complexification. So in this case.
Yes. So this is the analog of complexification. So this x bar is just x times over the spectrum of fq, spectrum of fq bar. Okay. So now let's let me say a few words about counting points over finite fields. So Weil conjectures. It's your home assignment for today. So formally everything is in your home assignment, but let me just say a few words, repeating what is there. I hope everybody knows Riemann zeta function. Am I right? And then what is the definition?
Series.
Yes.
Combination numbers n to the power minus s.
Right.
Or the product of
Yes. The product over all p.
prime numbers of
Yes.
1 minus p to the power minus s.
Right. Inverse. Yes. Thank you. Absolutely. And now you may note that this product goes over all closed points of the spectrum of Z. Yeah, there are maximal ideals of spectrum of Z. There is one generic point, there is spectrum of Q, but we only are interested in this. And then what is this P? This P is the maximal ideal. What is this P? This P is, the cardinality of the residue field. There's a residue field, K, P, and this is just F, P. Okay, so here we have places, just points, but now we cannot multiply points. We have to multiply some real numbers or integers or whatever. And the relation between this P and this P is that this is the cardinality of residue field of this point. Okay. Now in this formulation, it is very general, and you can consider it for arbitrary scheme at all. So as a finite type scheme over the integers, So in this basic Riemann case, we have just spectrum of Z. But we can have essentially anything else. And then we define, well, maybe not S is a bad notation, sorry. Y maybe. Zeta Y of S, by definition, is just the same thing. It's the product over all points, closed points. And here we have 1 minus n of p to the power negative s inverse. So once again, n of p is the cardinality of the residue field Kp. Okay. Residue field Kp. Well, once again, we have this OP modulo the maximal ideal MP. Yeah, the fiber of the structure sheaf at this point.
In the scheme of finite type,
Yeah, it guarantees that this is a finite field. In principle.
It means what? That the structure sheaf gives us finitely generated algebra.
Yes. Yes. Uh-huh.
The definition.
Finite type? Yes, absolutely. Okay. So this is some definition, but we will be concerned with one special case where this. So you may think of spectrum of Z as the collection of points like 2, 3, 5, 7, 11, and then there is this thick point Q, and so on. And now our scheme fibers over this spectrum, so it's our Y. But there is one special case where it all consists of just one fiber. So X is a finite type scheme living over just one point P. So it. Pardon me?
Q is the generic point.
Yes, Q is the generic point. Yeah, or spectrum of Q, maybe I should say. Okay, but I have just like this. This is our P, and there is nothing else, but everything lives here. So this is X. And so in other words, it means that X is a scheme over the spectrum of finite field of Q, and Q is some power of the prime number P. And is again finite type.
What is the same?
Because this point is nothing but the spectrum of Fp. So it
You somehow identify the point with
yes,
with its with a fiber of structure
yes.
of this point.
But this point is the spectrum of Fp. Okay. But well, okay. And in this case, you may rewrite this definition of zeta function. Namely, you may change the basic variable, because you see all the points that will be occurring here will be of the sort q to the power r for some r.
Once again, could you please elaborate what is Q? So I get that in our case we have P equal to 7 in this variable.
Yes.
But what's Q?
but this x, well, you see, if x goes to spectrum of F49, for example, then this also goes to the spectrum of F7. So this projection may factor through some bigger finite field, and we choose
The maximal section.
yes, the one it factors through. Okay, so once again, we start with a finite type scheme over FQ. So the typical example is projective scheme. Cut out by some homogeneous polynomials with coefficients in FQ. Okay, this is a typical example of a scheme over FQ. Okay, and then
Is a topological space?
it's well.
Projective spectrum.
Yeah, there are some ways to construct it, but well, it's a closed subscheme. If you understand what is projective space over FQ as a scheme, then this X is a closed subscheme cut out by some equations.
But it is a scheme over Z.
Yes, certainly, because well, it just lives in one fiber. It's a, well, for stupid reasons, it's a scheme over Z. Yes, in fact, everything is a scheme over Z, but many schemes are not of finite type over Z. But this particular one is of finite type. For example, the spectrum of C is not of finite type over spectrum of Z. Spectrum of Z is the final object in the category of schemes, but this is incountably generated, so it's not of finite type over spectrum of Z. Okay, so for example, X bar, as here, lies in the projective space over FQ bar, and it is cut out by the very same polynomials. Okay, so the equations are absolutely the same, but the ambient scheme is different, and so this scheme is also different from X itself. But well, in terms of equations, it's just written by the very same equations. For example, no equations at all. Okay?
Coefficients in FQ bar or FQ?
Well, the initial ones had coefficients in FQ. Otherwise, your scheme would not be defined over FQ. But now they lie in FQs, in particular in FQ bar, because FQ lies inside FQ bar. So you can consider the very same equations, but in the ambient project space over FQ bar.
Taking these equations in Z, in the integers, can we also do that and cut out our scheme in the integer projective space?
Well, I don't know. For example, you can consider the equation in P1, like X squared equals Y squared. Yeah, then certainly it defines something over whatever. You may write z here or fq here or whatever, r, whatever. It makes sense. But if I write an equation like this, square root of -1, then it would be nice over, say, f5, but would not make sense over z or over f3, because f3 does not have square root of -1.
This
So-
scheme would not have points, z points. Yes.
No, just not that it doesn't have these points. It does not make sense, because this thing does not make sense. There is no square root of -1.
Okay, but take the scheme over f5.
Fine. Let's take the scheme over f5. Yes.
And this has points over f5 bar or
Oh, absolutely, yes. That does have many points. Well, in fact, it has two points, as far as I understand. Yeah.
over f11, for example.
No, but over f13 it does. But doesn't matter. Just you need to take some coefficients in your ground ring. So if you somehow manage to assign some meaning to these coefficients in your ground ring, then really, yeah. Okay, so let's. I don't know. You have to define your scheme. You may define it over integers or over whatever you want, but you need to give some definition. After you gave definition, you may consider it over its domain.
And this scheme, how can we understand that it's actually of this sort, that it's vectors from one point?
That all the residue fields are of characteristic P.
And if it is projected and cut out by polynomials, then we understand it.
Mm. Mm. So if you start from projective space over integers, then you cannot cut out just one fiber. You cut out horizontally, so to say. You cannot write down equations over integers that have only one solution, namely prime number 2. So
Homogeneous equations.
yeah. Okay, so let's consider this zeta function. And in case we live over one particular point P, all the residue field cardinalities here, they are powers of one and the same thing, of Q. And for this reason, you just changed your variable. So in this setting, once again, when we are over finite field, so we take t, that is q to the power negative s. So s was the variable of zeta function. And now we take this new variable, and then we say that the zeta function of x that is defined here is also, it's also zeta, but capital zeta. And now it's cursed, but still we cannot change the standard notation. So it's zeta of x and t. So t is this q to the negative s. And this is just the product, if you wish, over all the closed points of x of 1 minus t to the power, degree of s of x inverse, and the degree of s of x well, how to say, q to the power degree of x is the cardinality of the residue field here.
There should be minus.
There should be minus.
No.
No, the minus, one minus is here, another one is here. No other minuses. Okay, and then our running title is counting points over finite fields, and we did not really count points so far. Yeah, so I want to give a relation to counting points. And there is this lemma, if you want, that this zeta function is the exponent of the sum from r equals 1 to infinity and r t to the power r over r, where and r is the number of points of x bar defined over f q to the power r. Right, so we have this x bar like this, and once again, from the point of view of equations, nothing happened. We just had something cut out by equations, and we may study its points over the ground field FQ, but we may also study its points over its solutions, just solutions of these equations over bigger fields, or field extensions. Okay, so it will have finitely many points over the initial ground field FQ, or maybe no points at all, but at least no more points than the projective space itself. Projective space itself has how many points? Like q to the power m plus q to the power m minus 1 plus so on plus q plus 1. Okay, as many points here.
Okay, x is projective.
Well, if x is projective, yeah, then this will be the upper bound. This works in utmost generality, yeah. But just to
X is of finite type.
it's of finite type, yeah. So the most interesting examples are of projective schemes when you have to count points of something particular, like elliptic curves, or curves of higher genus. So once again, you start from just points over FQ, and you have n1 points over FQ. Then you can count points over FQ squared, and you'll have more than this, just n2 points over FQ squared, and so on. So you just count the number of solutions of your equations over bigger and bigger finite fields. These are some finite numbers, and this is some generating function of these number of solutions. Okay, and I don't know, maybe let's take a vote. This is your exercise number 1A for today. So maybe I shouldn't tell you the solution. But if you all vote anonymously, I can give you a solution. But then, unfortunately, everybody else will hear the solution, and maybe somebody wouldn't like to. So it's rather elementary. No big deal. So maybe I skip it. Yeah. Okay. I mean, just if you know the formula for logarithm and formula for exponent, if you know that logarithm of product is the sum of logarithms, then you are done. Okay, so that's it for zeta functions, but still maybe let's do just one most stupid example. So we essentially did it already for projective space, but maybe just for projective line. So if x is just p1 fq, then what is nr? What is the number of points over finite field fq to the power r? So the answer is what? Q to the power r plus 1, I would say. Yeah, that's it. Right? Agreed?
A fine line and one.
And yes, a fine line and one infinity point. Yes, that's it. Fine. So let's compute the sum of q to the power r plus 1 t to the power r over r.
Once again, we are not counting the closed points.
Yes, the closed points, yes.
Here it is not emphasized.
nr.
Is the number of points.
Oh, sorry. Yes. So closed points, right, absolutely. So, what is this? This has two summands. First of all, q to the power r, t to the power r over r, plus the sum of t to the power r over r. And can you sum this up?
It's logarithm of q t plus 1 plus t. Minus, 1 minus q.
Yeah. Like this. But then you have to exponentiate, you see? So the zeta function will be, and also, in fact, here you will have minuses, minus log. So it'll be 1 over 1 minus t times 1 minus qt. Okay, and in fact, the zeta function of p to the power m will be very similar, 1 over 1 minus t, 1 minus qt, and so on, 1 minus q to the power m, t, like this. And you can easily compute the zeta function of Grassmannian, for example, and something like this. But which is more interesting if x is a projective curve of genus G over Fq. Then the zeta function of x will have always the same denominator, and in the numerator you will have also a polynomial, but of degree twice the genus, 2g. So p of t, and p of t will be the product of linear factors. Well, there will be some complex numbers, but in fact, this polynomial will have integer coefficients, and it will be 1 in degree 0. Okay, and so all in all, your zeta function is a rational function. Like, and well, more specific than this, but at least it's some rational function. And this is a theorem of Algebraic. For curves, yes. Yes, for curves.
Is this P connected to the Hilbert, or is it some special?
No, absolutely, no. It doesn't depend on the, as you see, it doesn't depend on the projective embedding. Hilbert polynomial does depend on projective embedding, and this one is something inner.
The function is computed via what?
How to prove this?
How to compute the form of this zeta function?
I don't know how to compute. How to prove this claim or what?
How to compute explicitly this pi of t, this polynomial?
No, not explicitly. How to check, how to prove that it has this form?
Well, just solve your home assignment for today. It's all there. Okay, and it's funny that Algebraic is one of the greatest French mathematicians of the 20th century, but this particular theorem was proved by him, well, many times, but it was in 40s, maybe in 43, for example. And at this particular moment, he was serving his sentence in French prison for avoiding the military draft. So it was during World War II, so he should have been an officer of French army fighting Germans. But he chose to escape France to Finland, and there he was detained and almost executed as a Soviet spy. But then he was transferred to Sweden, to England, back to France, and finally detained arrested and sentenced for escaping the draft. So while he was in jail, in prison, he proved this theorem. And then he finally, well, served his sentence and went to US, and there he eventually ended up at the Institute of Advanced Studies in Princeton, and there maybe sort of chairman was Herman Weyl at this time. And then Herman Weyl said that he will apply all his influence to send Algebraic to American prison, so that he proved something equally great next time. Yeah, but unfortunately this did not work. Though they did prove very many great things, and after World War II as well, but he was never detained in US. Okay, so somehow in this exposition I suggest in home assignment, this very statement is really not proved. I mean, it's proved modulo some technical claim that is not easy in this exposition. But the other one is proved. Though in general, I mean, you see, for higher dimensional varieties, you also get rational functions. And there are some general arguments by Dwork and Grothendieck and some other that establish rationality in general. But there is one extra claim that I will formulate presently, and that is very, very hard to prove in general, but for curves it follows from this Castelnova-Severi inequality, and so you will prove it soon. Pardon me? Yes?
According to the formula, so the zeta function is not only in Qt but also in Zt.
Pardon me? Say it again? Just say it again, please.
It's like the P of t is a
Polynomial?
with integer coefficients.
Yes, with integer coefficients, yes.
And, and so is the like denominator.
This is numerator, this is denominator.
Yeah, but both of them are polynomials with integer coefficients.
Right.
So it's not only in Q of t but also Z of t.
Well, I don't really know what's the meaning of z of t. It's rational functions, so I don't know the meaning of z of t. Like I have 2t over 3t. This will be 2 over 3. So it's not an integer. So, Untitled theorem, but it's called also Riemann hypothesis. That the absolute values of all those inverse roots are square root of q for any I. And if you remember that t is q to the power negative s, it exactly corresponds to the classical Riemann hypothesis. That the zeros of the classical zeta function are at the real part of s equals 1/2. Just literally this statement. Though in this case, the zeta function will also have poles, not only zeros. Well, in fact, the usual zeta function also has a single pole at 1. And this one also has a pole at 1, but one more extra pole at negative q, at the q inverse. Okay. And so this is extremely hard to prove in general. For curves, I mean, we studied for more than half a year, and now we can prove this for curves. But for higher dimensional varieties, it's extremely hard. So it was not even proved by Grothendieck. So Grothendieck somehow developed algebraic geometry in order to prove this, but did not prove this himself, but it was later proved by Dely. But it took like thousands of pages of foundations by Grothendieck to develop this theory to prove the Riemann hypothesis in general for higher dimension. But for curves, it's within our reach after half a year of our studies. Okay. So this is it for counting points. But somehow this point counting is very, very important. I mean, as far as I understand, currently almost all advanced codes, like in KGB or central bank or whatever, they're based on this point count. I mean, namely on this Riemann hypothesis. In fact, even the not advanced codes, like based on products of two big primes. I mean, their security is based on the classical Riemann hypothesis. Yeah, that the primes occur not too often, and there are more advanced codes based on elliptic curves or finite fields, and that they are based on this Riemann hypothesis for elliptic curves. Though this Riemann hypothesis for elliptic curves were proved before Untitled. It was proved by Hasse and maybe Emil Artin, like 20 years before this, for elliptic curves.
What is the claim in this hypothesis? The right-hand side does not depend on...
That they all have Yeah, the same absolute value. And again, if you just read your home assignment, you will see some consequences of this. So it's a very sharp estimate on an R. It says that an R is approximately like for positive line, so it's like q plus 1, but it's not, since it's not positive line but some curve, it's approximately this, but this approximation is very good. It's good up to some square root of q. Okay. And the same for classical Riemann hypothesis and number of primes. You know there's distribution law for primes. It says that the number of primes up to n is approximately logarithm n over n. Yeah, but then you want to count the error, and this error is the error estimate is via the Riemann hypothesis. Oh, sorry, it's q to the power r. Sorry. Mm-hmm. Yes. Mm-hmm. Yes. Okay, so now we forget everything about this. And we start a big new topic. It's about Hilbert schemes. And it was all developed by Grothendieck somehow in the very beginning of his work on algebraic geometry. And indeed this Hilbert scheme construction is very, very foundational. So majority of constructions in algebraic geometry are based on this. And we will study this for maybe for the whole April. Well, these are solutions of some moduli problem. Well, moduli problems. Well, in some exercises, we proved, or maybe you will prove in your home assignment. Unfortunately, so I already gave you home assignments for the whole of April, and somehow it would be best if you solved all of them simultaneously right away, tonight. So somehow I'm referring to all the April exercises, unfortunately. So I mean, you maybe at least you can read them. You may submit the solutions towards May, but at least read them, because I will constantly use it. So, for example, given any projective scheme, say over a field K, it's okay to have just algebraically closed field K as before. The closed subscheme, and then we can consider this Hilbert polynomial. Well, maybe let me call it H x of R. And this is, well, there are various definitions. Say is the Euler characteristic of x with coefficients in OX of R. So it's embedded into projective space. On the projective space, we have those standard invertible sheaves O of R. We can restrict them to X and compute the Euler characteristics. Okay, and now it's really a polynomial in R. For example, its degree equals what?
Dimension.
Yes, the dimension of X. And then various other characteristics of X can be read off this polynomial. For example, degree of X. And this was more or less in exercises in last semester, but also, well, we didn't have Euler characteristic yet. But if R is big enough, then there are no higher cohomology. So for R sufficiently positive, this Euler characteristic is nothing but the dimension of global sections with coefficients in this very ample sheaf. And in this form, it was studied last semester. But it's always polynomial. That's the key point. That it's not the dependence on R is not random, but it's just a polynomial of this degree of dimension X. Okay, and now we proved. For example, yeah. Mm-hmm. Or from Cauchy resolution, or I just look it up in the home assignment. So we can deform X. A flat family. Some Bayes scheme. So this X lies in projective space over S. And then, since the family is flat, the Hilbert polynomials of all the fibers XS for all the points in this base are the same. We proved this. We proved that in a flat family, the Euler characteristics do not vary. They're constant. Yeah. So if like this is pi, then XS is the pi inverse, of S. So you just imagine this like collection of fibers that vary in a flat family over this base. Yeah. Here it doesn't really matter, but we can start with algebraically closed field K. Okay, if you want, it's algebraically closed. Yes.
Просто получается, что мы как бы формулируем утверждение сейчас, которое мы доказывали в конкретном случае.
So okay, K is algebraically closed. You will see later that it doesn't matter, but at this point, it can be safely assumed algebraically closed. Pardon me?
PS is some fiber product.
Well, it's just, over K times S over, no, well, it's just, if S is the scheme over K, then I don't need to write anything here.
Product over spec K.
Yes, but yes, okay. Flat. Flat means that the structure sheaf is flat over the structure sheaf of S.
You mean that pi is flat?
Pi is flat, yes. Mm-hmm. Pi is flat. Mm-hmm. Okay, so in flat families, the Hilbert polynomial does not vary. And this moduli problem I mentioned, this moduli problem is all the projective schemes with a given Hilbert polynomial.
What is a moduli
Let me formulate it. So this moduli problem is an assignment. So let me fix a polynomial like this. So I fix so I think it's called numerical polynomial. H of R. I mean, it is with rational coefficients, but the values are all integers. Or maybe it's called integral, and I forgot. In fact, you may fix any polynomial at all, but there will be no schemes with this polynomial. Yeah. So fix such a polynomial, and now consider the following functor, Hilb, well, H. There's a functor from just schemes to sets.
But we consider relative schemes here.
No, so far not. No. No.
Over X. X twice over X.
Yeah. Maybe I should. No, it's fine like this. So this functor takes a scheme S to the set of all closed subschemes X P and S, like this, such that the Hilbert polynomial of any fiber is just H. Maybe I should say flat over S, but in fact we will see during the proof that this rigidity of Hilbert polynomial guarantees that it's flat. If I have a flat family, then the Hilbert polynomials are constant, but the converse is also true. If we have a family with constant Hilbert polynomial, then it's flat. Okay? But it doesn't matter, I can require this flatness additionally.
So again, given the scheme, I can fit it with
The set of all closed subschemes, why not?
M large is also fixed. Or does it vary?
It is fixed. Okay, it is fixed. So maybe I should somewhere put it, but like this. Okay, and so then there is the major theorem by Grothendieck. Around 60, but maybe formally 62, that this functor is representable by a scheme, well, it's called Hilbert scheme. But it is also projective. It does not lie certainly in this space. It lies in some huge projective space. But
Once again, this phi, which so we consider the set of all these
set of all what?
Yeah, so we can,
X?
yeah, X.
Yeah.
X. So we consider them after.
Nothing, just the rigidity is given by this closed embedding. So they're given as closed subschemes of projective space.
Even if they are isomorphic.
Not abstractly, but just as closed subspaces of projective space. Closed subschemes of.
If they lie inside this space differently, but they are isomorphic, we still consider them as
Different, absolutely different, yeah. What matters is this closed embedding in the projective space.
Now we fix this projection to S.
Well, it's given here, the diagram commutes. For example, the Hilbert scheme of 2 points. Yeah, 2 points are always 2 points, but it depends on how they are embedded into the embedded project space. This X might, yeah. For example, if the Hilbert polynomial is just 2, it's just constant polynomial 2. So then we're speaking of just 2 points embedded into project space. They're always 2 points, but embedded differently. And also they can merge into dual numbers. And then there's one thick point embedded into project space. The spectrum of dual numbers. The spectrum of k of epsilon modulo epsilon squared.
You're speaking about this representing object already.
No. Just consider the example. H equals 2. Then, say this Hilbert scheme, or function or whatever, say P1 and 2, has 2 strata. One is just P1 times P1 minus diagonal over Z2. Yeah, the 2 points, distinct points. And another one, well, it's just diagonal, but somehow this corresponds to subschemes, spectrum of dual numbers.
What is the two one?
Just, well, S2 if you want. This embedded into P1. Okay? So just 1 point, but thick point, with the point with a tangent vector.
No, you cannot see it.
Hmm?
If you can explain
What?
why it is true, why this object that you described does represent this functor.
Well, it will take us, again, the whole April to prove this theorem, but after you know that it's true, then what else can you have? You can either have two distinct points, reduced. Well, here it is, they are distinct.
But the functor is representable, meaning that
There is some, well,
it is the same as
yeah, this,
Hilbert's.
yeah. So Hilb H BM of S is the same as just morphisms of schemes from S to this representing scheme.
So this functor is contravariant.
Oh, certainly yes, because you can pull back, right? You can pull back. If there is S prime, then you can.
We need to use the property of flat morphisms that they are stable under pullbacks.
Well, I think here if everything is clear, but
X over S was flat.
yes,
We need X prime.
but yes,
Prime to be flat.
yes, it will be yes. So that's the theorem. That's the most simple example, and let me say one more word that the closed subscheme well, maybe not the, but a closed subscheme like X in Pn is nothing but the quotient sheaf O Pn projects onto Ox. Okay. So in other words, this problem we discussed, this moduli problem, is equivalent to another moduli problem. Just classify all the quotient sheaves this moduli problem is equivalent to another moduli problem. And so here this other modular problem is the set of all quotient sheaves so I have P, maybe O, P, N, S onto F. So these F are flat over S, and the Hilbert polynomial, that is Euler characteristic of F twisted by R, Fs, is always the same polynomial h of R for any fiber. Okay, so we just reformulated this problem. Okay, and this reformulation is on the one hand immediate, straightforward. On the other hand, it seemingly loses some information because the structure sheaf of a scheme was a sheaf of rings, right? And here we absolutely forget this ring structure. But just it happens so that all the quotient sheaves of the structure sheaf are automatically, necessarily sheaves of rings. But this ring structure is irrelevant for the problem, somehow. So we may forget it. That's the main message. And so this Grothendieck's theorem about Hilbert schemes follows this way immediately from another, more general theorem by Grothendieck about quad schemes. And we will, for the next month, forget about Hilbert schemes and only work with quad schemes. Quad schema in Russian. Yeah. Oh, absolutely. Yeah, that's the whole content of the whole course. We prove nothing, right? Given a locally free sheaf, say E on Pn over K, and again polynomial H. There is this quad functor, Pn epsilon E H of S, the set of quotients Oh, it's my idiotism, sorry. So again, we have scheme S, and we have P and S, and here we have ES. That's just the pullback. It projects to Pn, and here we have E, so we just pull back. And this ES projects onto F, and the Euler characteristic yes of F as twisted by R is H of R for any fiber.
ES is a
Pardon me?
product of sheaves. No?
It's the pullback. Well, there's a projection to the to project space over field, and we just pull it back here. So it's trivial in this family. But the quotient is variable in the family. We only need that this is flat over S, and the Hilbert polynomials, all the fibers are the same, given by H. So this is representable by a projective scheme quad E, H, like this. Okay. So if you apply this just to the structure sheaf of projective space, then you get the theorem about Hilbert scheme. And quad schemes are generalizations of Hilbert schemes. So we will prove the theorem in this formulation, and it will take us quite a long time. But somehow you will see how the concepts we studied work in real applications.
Could you please give some literature?
Yes, so the best literature is just some collection of 6 reports of Grothendieck in Seminar Bourbaki, and it's called Fondement de géométrie algébrique. So 6 reports at Bourbaki seminar. Yeah. And it's by Alexandre Grothendieck. But then, like 10 years ago, it was just translated into English, and it's called Fundamental Algebraic Geometry. And there are many authors like Barbara Fontecchi and Lothar Goetze. Pardon me? Who are these people? Some modern algebraic geometers, and Nissim Nitzur, and Angelo Vistoli, and many others. But this is available. Well, this is available. This is available. So this is in French. This is in English. I don't know. Well, just the notation itself is everywhere, like in Wikipedia, but the proof I mean, if you want to find solutions to home assignment somewhere, then I forgot.
Нет, именно про то, что мы с вами не домашнего.
But the notation is everywhere, just it's in Wikipedia. Or it's the very, very standard notation. It's used everywhere, absolutely everywhere. For example, you may read in the introduction to the famous paper by Pierre Deligne, the proof of Weil conjecture 1. So I forgot a good reference. Certainly there is an original paper by André Weil, and also there is some elementary proof of this rationality by Stepanov, even in Russian, like for 40 years ago. But I forgot the exact reference.
Степанов это его монография или что?
Also, it was some paper, maybe there was some book, but originally it was just a short paper. Thank you. Just one moment.